Okay, so chapters 4 and 5 are all about probability. So let's go ahead and get started. So in probability, we have first an experiment. So we're starting with some vocab here. And that is a process that results in one observation. Let's see if I can type here. No. Nope, looks like we're gonna have to write. Okay, a process that results in one observation. Okay, so we have a result. So you run an experiment and the observation that you have is called a result. Okay, and that result is called an outcome. So we can say an outcome or a result. Okay, and that is an observation obtained from an experiment. Now, in an experiment, you have a sample space, which is your collection of all outcomes from an experiment. Okay, now in the sample space, I'm going to give you an example of that. Can anybody else hear me, or is it just Christy here? Hold on one second. Let me check things. So, okay, so everybody else can hear me, which means Christy, it must be you. Okay. Let me give you guys an example of a sample space. So let's say you run an experiment to see the outcome of flipping a coin. So you flip on a coin, you have two possible outcomes, heads or tails. The sample space for that outcome would be like this. So you're going to use like curly brackets, heads, comma, tails. Okay, that's the outcomes. You can either get heads or tails. So that's your sample space. So the collection of all of the outcomes that you could get when you run an experiment. And that's what it'll look like. An event is one or more outcomes from an experiment. Okay, so we say the event is the outcome. So the event happens, we do heads or tails, and the event outcome is heads. Okay, so that's our event. We name the event capital E. A simple event includes one and only one outcome. So it's a single event. And then a compound event is going to have more than one outcome. And then probability. So probability, the technical definition here, is a numerical measure of the likelihood of a specific event to occur. Okay, so how likely is it that I'm going to get heads when I flip this coin? Okay, that's the probability. So a numerical measure of the likelihood of a specific event to occur. Okay, the probability, when we're doing probability, you might see it in the news and things like that. You see it as a percent. Okay, and we're going to be doing probability. When you're doing it in statistics, it's actually always between 0 and 1. So we keep it as a decimal when we're doing statistics. But when you're relaying it to everyone or to the population, you would convert that to a percent, just because it's easier to understand. Okay, we have 3 approaches to probability. So you have classical probability, which can also be called theoretical probability. Okay, and that is going to be what should happen basically in theory. So a very easy way to go about explaining this is going back to the coin toss example. So theoretically, every time I toss a coin, I have a 50% chance of getting heads or tails. Okay, so or 0.5 would be my probability. But let's say I rolled or I tossed the coin 100 times. How likely is it that I'm actually going to get 50 heads and 50 tails? Okay, might happen. In theory, that's what should happen. So theoretical probability is the theory of it, okay, based off of the sample space, not based off of running an actual experiment. Okay. So classical probability for equally likely outcomes is given to you as an equation like this. So P of E, so parentheses E, so probability of the event happening is the number of possible, number of times event occurs okay, over the number of total outcomes. Okay, if the event has equally likely outcomes and its sample space has equally likely outcomes, the theoretical probability is denoted like this. So it would be the number in your sample space of that happening by the total number of outcomes. For example, let me make this easy for you. The probability of getting heads. Here's my sample space for this. My sample space is heads or tails. So let me come, we'll go up here. SS for sample space, heads or tails. How many times in that sample space do I see the letter H? One time. How many total outcomes are there in the sample space? 1, 2. The probability of getting heads is 1 over 2 or 0.5. Okay, so how many times in the sample space does that event occur? And then how many total outcomes could there be possibly? So for example, a die is rolled once. Find the probability of getting a number less than 5. So the way we're going to write this is going to look like this. You're going to go P, and then your event is that you get a number less than 5. So we just say less than 5. Okay, so that's your probability. Well, let's look at this sample space. Okay, in your sample space, you've got on a dice, how many sides are there on a dice? 6. Yeah, there's 6 sides to a dice. So your sample space here would be 1, 2, 3, 4, 5, 6. Okay, well, how many of these are less than 5? Good, 4. Yeah, these all, 1, 2, 3, and 4, are less than 5. So there's 4 ways that you could get a number less than 5, and there are 6 total possible outcomes. And then you would reduce that. You could make that 2/3 or just do the fraction. Okay, and we would do, let's do 3, what do we got? What do I have here? 2 decimal places, 2 decimal places. So it was 0.67. Okay, so that's your probability. What does that mean? In layman's terms, if I roll a dice 100 times, theoretically, 67 out of those 100 times, I should get a 1, a 2, a 3, or a 4. The other 33 times, I should have a 5 or a 6. Is that what's actually going to happen? Probably not, but that's what should happen, okay, because of the way the dice is and how many occurrences there are or chances there are to get a number less than 5. You're dealt 1 card from a standard 52 card deck. So if you have not played cards, you might want to get familiar with this. Okay, there's 52 cards in a deck of cards. Find the probability of being dealt a king. So I'm not going to write out the entire sample space for a 52 card deck, but how many kings are there? 4. Yeah, there's 4 kings. You've got P of K for king. You've got hearts, spades, diamonds, and clubs. So there's 4 kings, and there's a total of 52 cards in a deck of cards. So you could take that and you can make that into a fraction, or you can reduce that. Now in your calculator, you can reduce if you just hit the button that says math right here and then enter. So that will be 1/13. Or what was that fraction? That was 0.007. We'll do 3 for that. 0.077. So the probability of being dealt a king, 0.077. Okay, then we're going to look at experimental probability or empirical probability. So write this down right here. Okay, now what that is we go back up to this dice example. Okay, 0.5. So if I roll the dice 100 times, 50 times it should be heads. Most likely that's not going to happen. So the experimental probability is what actually happens once we run that experiment. Okay, so what happens when an experiment is run? Okay, now in that you have the relative frequency will give you the probability in an experiment. So that's going to be the formula F over N, where F stands for the frequency of the event, so how many times the event occurred in the experiment. And then N is going to be how many experiments you ran. So your sample size, which we'll put in parentheses, total number of experiments. Okay, so let's say, for example, I flip a coin 100 times. And out of the 100 times, 55 times I roll a heads. Well, then in that case, my experimental probability of heads would be 55 over 100, or 0.55. So that's all that is. So when you're given an example, you have to see, did they say that they actually did the experiment or not? The probability formula is the same, okay? It's how many events that actually occur versus, okay, this total sample size. So we'll look at some examples for that. It's very, very easy to differentiate. Subjective probability, we don't really do much with that, with the calculation, but you do need to know the definition. So it's the probability assigned to an event based on a judgment. Subjective judgment. Experience. Or belief. So you're not actually running an experiment, you're just assigning a probability, basically just making it up. So that's subjective probability. All right, and then the law of large numbers tells us the difference between theoretical probability and empirical probability. So this will tell us that the greater number of times an experiment is run, the closer the theoretical probability will be to the experimental probability. So the greater the number of times an experiment is run, the closer the experimental probability will get to the theoretical probability. So for example, okay, I pull this up here. So let's say we toss the coin 10 times. Okay, here's my results. I get 1, 2, 3, 4 heads, 6 tails. Okay, so that's a 0.4 probability for heads. We'll do that. Okay, let's add another 0 to that. I'd possum 100 times. Well, now I get closer to that 50-50. Do them 1,000 times. I think that was almost the same. Okay, so 1,000 times, closer you get to 50-50. Oh, cumulative stats. There we go. Let's do 100,000 times. This might take a minute. Oh, 1,000 is the most that we can do. Okay, so 1,000 is the most that this actual one could do. But that will be the law of large numbers. The more experiments you run, the closer that probability from your experiment is going to get to the theoretical probability. So when you're running an experiment and you are doing a probability based off of that, you want to have the largest sample size that you could possibly get. Okay, that way it can be more accurate. So just a little chart here for us. Go here. We have theoretical versus experimental or empirical. It's the same thing. They're interchangeable. So theoretical, you have no experiment. Okay, it's based off of the sample space. This is what is supposed to happen. Okay, and then in empirical, you have an experiment is run. And then this is what actually happens. The more experiments you run, the closer the numbers will be to each other. The sample size should be at least 30 when you're running an experiment. All right, and we have some practice problems. So I'm gonna let you guys take a look at these for a few minutes and then we'll come together and work on them. I'll go through them with you. All right, so yeah, cards. If we're not really familiar with cards, it might do you well for this chapter to play a little solitaire, just to get familiar. But you've got 4 different suits. So you have hearts and diamonds, those are both red. Spades and clubs, those are both black, and it goes 2 through ace, or you could say ace through king. Ace can be either high or low. Where you know, the number cards represent the number, and then you have face cards. You have a jack, queen, king, and then you have ace. Okay, so there's 13 different cards that you could have, and then 4 different suits, so for a total of 52. So 2 of the suits are red, and then 2 of the suits are black. So for a black card, you would have a total of how many different black ones that you could pick out? Yeah, 26. So there are 13 clubs and 13 spades. So that would be 26 out of 52. Half are red, half are black. So it's 1/2. Okay, which would be 0.5. A spade. So there's 4 different suits. Each suit has how many? 13. 13 cards out of 52. And that would be 1/4. Okay, so you could also go just 1/4. There's 4 suits. One of them is spades. And that would be 0.25. All right, a jack. How many jacks are there? Yeah, 4 jacks. One of each suit out of 52 cards. That's 1 in 13, which we did was 0.077. And then a black jack. Yeah, 2 black jacks. You got either spades or clubs out of the total of 52 cards. So 2 out of 52, or 1 out of 26, which as a decimal gives us 0.038. All right, and then a face card that is not a heart. So you want to think about the possibilities here. You have Jack, Queen, or King, but not a heart. So you'd have 3 here. So either a spade, club, or diamond. 3 here, spade, club, or diamond. 3 here. So yeah, that would be 9. Again, out of 52. So that gives us 0.173. Okay, and then of course these are all just in single experiments. So this isn't me taking a deck of cards and each time, we're going to get to that later on in the chapter. This is a single one, meaning, okay, I have a full deck of cards each time I'm flipping one. I wrote this here for number 2. The sum of probabilities is 1, just to help you out there. I don't know. I don't think we went over it. But yeah, when you're doing the probability of a single experiment, the sum of all of the total possible outcomes that you could have is going to be 1. So I'm tossing a coin. Okay, I have a 0.5 probability of heads and a 0.5 probability of tails, the sum of which is 1. So in a single experiment, the sum of the probabilities, we add them all together, would be 1. So when I'm looking at this table, and M&Ms are really good for probability. I think we discussed that before when we were talking about standard deviation. They're good for probability as well. So this was pulled from the M&M website a while ago. I think it's been about 10 years since I pulled this data. It's probably pretty similar. But the missing probabilities here. So in a probability table, if I add all of these numbers together, I should get 1. So if I'm missing 1, I can find the missing one. So if I add these together, okay, I get 0.9, and then the missing one would be 1 minus 0.9, so 0.1. So there should be a 0.1 for green M&Ms in this table. And then for the peanut ones, we're missing the yellow. So let's add these probabilities. That's going to give us 0.71. And then 1 minus 0.71 will give us 0.29. Okay, so our table is complete. Now we want to answer some questions. What is the probability that a plain M&M is red or blue? So this is actually a type of probability that we call I'm looking on for the actual definition here. Joint, that's not joint probability. Marginal probability. Okay, so it's a different type of probability, but we're really just adding the probabilities together. So we can still do this with a simple probability formula. You want to make sure you're looking at the right chart for plain M&Ms. So you have the probability of a red M&M is, and this is on the plain table, 0.02. The probability of a blue M&M is 0.1. And if we add those together, okay, the probability I either get red or blue is going to be 0.12. What's the probability that a peanut is red or blue? I'm doing the same thing here, but now I'm looking at the peanut table. So here I have, let's see, peanut table, red is going to be 0.01 and blue 0.3. And if I add those together, I'm going to get 0.31. And then see what is the probability that a peanut M&M is not brown. So you have two ways to do this. Since the sum of the probabilities is 1, what we can do here is you could do 1 minus the probability of brown. Okay, and that would be 1 minus 0.2, which would give us 0.8. Or you can just take this chart here and you can just add all of the ones that aren't brown. And you can add all of those together. And that should give you a 0.8 as well. So you have two ways that you can go about doing that problem. And that should be it for 4.1 and 4.2. We're going to go into the marginal probability a lot more when we go to 4.3, but this is just kind of an introduction to it for now. Does anybody have any questions? Okay, well, if you do have questions, stick around. Otherwise, you guys are free to go, and that's all I have for you for today.